All right, so here's the video that I promised I would make. So far we've looked at Newton's three laws. So again, we have the first law. So the first law tells us where we can use Newton's laws. So meaning it defines for us an inertial reference frame. So again, inertial reference frame is one where we can use Newton's laws, and that's when the velocity is simply equal to a constant. And then we also have the reference frame where we cannot use Newton's laws, and that's what's known as a non-inertial reference frame. And that's when the velocity is not equal to a constant, i.e. it is accelerating, may have a constant acceleration or non-constant acceleration, doesn't really matter, but it's just not moving with constant speed. And we know that in this case, we get fictitious forces. So in this case, we get forces that the observer would actually see that aren't actually forces. I mean, again, they are not real forces in the fact that we can't identify where they actually come from. And again, we'll look at this one in more depth later. Then we have the second law. So the second law, again, is a operational definition, which basically just says that the sum of the forces acting on the system is equal to the time rate of change of the momentum. Or again, we define the dots. So this is then going to be P dots. Right? Now, again, in the special case where the mass is equal to a constant, in that case, then we get the sum of the forces is our usual mass times the acceleration, or this is going to be equal to the mass times the first derivative of the velocity, or the mass times the second derivative of the position, or in most cases, I'm going to write this as the r vector as my position vector. So cool. So this is our second law, just an operational definition. And again, our third law. So the third law simply says that for an isolated system, then the force along the line that connects the two are going to be equal and opposite. Right. So again, we have an isolated system. So in this case, this is the force on 1/2, which is the force on 2/1. That's if they are attractive, or I can have this force here, F12, or I can also have this force here, F21, if they are repulsive, where these guys are separated by some distance of r. So again, we have F12 is equal to negative of F21, which automatically then implies to us that we have conservation momentum, which says that the net momentum is equal to a constant, where the net momentum is equal to the sum over all possible momenta. Good. Now, this is only true if we have a central force, i.e. what Newton's law actually abides by. So Newton's law, at least the third law, only works for central forces. If it's a non-central force, in this case, the change in momentum is not equal to 0. So in this case, our change in momentum is equal to the impulse. So J, which is the integral of the force, which in this case will be the external force acting on the system integrated over time from some initial time to some final time. So this is true anytime I have external forces acting on the system. So this would be true if it is non-central and or external forces acting on a system. There we go. Lost my brain there for a second. So external forces. So in this case, non-central basically means that, again, they will not be acting along the line connecting the two. So non-central is not along the central line. Now, we'll formally, as I talked about before, define what a central force is, but for now, we're just saying it's one that is along the line that connects the two objects, or I'm calling that the central line. So great, so these are our third laws. So now we want to actually talk about how do we calculate? So how do we calculate? So great. So we talked about the three laws. So now what we simply want to do is how do we calculate? So how do we find the dynamics? So how do we determine the dynamics of the system? So the way we determine dynamics is simply we're going to use starting off with Newton's second law. So we're going to start off with Newton's second law, which again says that the sum of the forces acting on the system is going to be equal to, in this case, we're going to look at specifically when the mass is equal to a constant. Now, we'll generalize this later when we start looking at rockets and things like that for non-constants masses, but for now, we're going to keep it that way, times then the second derivative of then our position vector. So let's talk about this. So basically, what this says then is number one, that dynamics boils down to, first, a knowledge of the forces. So we have to know the forces which are acting on some sort of system to determine the dynamics of the system. So that's number one. Number two then is we then have to solve in general a second order differential equation. Okay. Now, a lot of time we'll be able to split this up into two first orders. So I'm going to write that under here. So in many cases, we can determine, or we can actually, let's do it this way. We can split it up into two first order differential equations. So the first of the two is going to give us then the velocity. So we are going to integrate once. To get the velocity. And then the second one, we would integrate a second time. So integrate a second time to get the position. Now, things to know, we talked about this a little bit in class. So since this is a second order differential equation, we're in general going to have what, two constants. So since second order differential equation, we will have two integration constants. Now, these integration constants are what is going to determine the uniqueness of our differential equation. So every differential equation has a unique solution to it, as long as we know the boundary conditions or we know the initial conditions. It just depends on the situation. But this is what's known as the uniqueness theorem. So in this case, if we're doing two first order differential equations, our first constant is simply going to be the initial velocity, which is the velocity it has at t is equal to t initial. And then our second is going to be the initial position, which is going to be the position it has at the initial time. So basically, again, all it boils down to is what? We have to solve a second order differential equation, which in a lot of cases, we can break it up into integrating once to get the velocity as a function of time, and then integrating again to get the position as a function of time, where we pick up two integration constants, the first one being the velocity, and then the second one being the position. Now, note that, again, since we are dealing with differential equations and we're doing integrals and things like this, basically, yeah. So basically, we have a small sliver of differential equations we can actually solve, or a small sliver of integrals that we can actually solve. So in many cases, this may not be analytically possible. So many solutions to this second order differential equation may not analytically exists. So basically meaning that we cannot find them in closed form. So there's no actual function that this integral will allow us to be able to solve for. So in those cases, we have different ways we can actually solve this guy. So methods for solving. One is to do approximations. So when I say approximations in this case, what I mean things are like looking at close to a source, for example. So we're going to look at small distances and find what the solution looks like at small distances. Another one is we can look at the asymptotic behavior, which basically means that we're going to go really far away. So i.e. long distances. We can also do perturbation theory. Perturbation, which basically means that we're going to do a Taylor series expansion about some sort of small parameter. And then by taking higher and higher order terms, that gives us more and more detail on what's actually happening in those cases. So those are approximation methods. And then the last way we can actually solve this then is numerically. So things like Mathematica have what's called ND-solve built into it, which is a numerical differential equation solver, which allows us to be able to determine the solutions for this thing numerically. So in this case, we have to put in certain set numbers for our initial conditions, and then we can create plots based off of those to kind of see what the behavior of the system is, whether that is an angle as a function of time, or position as a function of time, or etc. So yeah, so basically, again, we have to solve a second order differential equation. Now, in this class, of course, everything for the most part will be analytically solvable, but that's only a fraction of what it is that we can actually solve, at least solve in closed form. Everything else we'll have to either do approximations for or solve them actually numerically using some sort of a numerical solver. So cool. So now that we know that, let's first look at a particular case. So let's first look at rectilinear. So rectilinear system. So this basically just means that all dynamics are in one direction. So all dynamics occur in 1D. Okay, so one direction, so one dimension. So in this case, let's simply call that the x direction. So things are just happening in the x direction. So what this means then is that Newton's second law then boils down to the sum of the forces, which is then going to be equal to, say, the net force, where the net force can depend on position, velocity, and, say, time, is then going to be equal to the mass times the second derivative of the position. So in this case, we have simply chosen that our direction is the x direction. Of course, we could have chose the y direction, the z direction, the bob direction, the star direction, doesn't really matter. But let's just say all of our dynamics are happening in one direction. So our second order differential equation breaks down to knowing the forces acting solely in the x direction, which is where all the dynamics are occurring, which in general, again, is going to depend on the position, the velocity, and the time. And then that's going to be equal to our mass times our acceleration, where again, in this case, we're looking at the special case where the mass is equal to a constant. So good. So from here, let's look at some special cases of this. Our first special case we're going to look at is the easy one, which is, let's say our acceleration is equal to a constant. So we want our x double dot here to equal a constant, which I'm going to call simply equal to a. So we have some sort of constant acceleration. Acceleration. So good. So let's look at this guy. So what do we know in this case? We know that Newton's second law says that in this case, my force, which is going to be my net force, and I'm going to drop the vector sign because it's only happening in one direction, is going to be equal to my mass times my second derivative, which is going to be the same thing then as my mass times my acceleration. So in this case, my acceleration then is simply going to be equal to what? My force divided by the mass, where this is my net force acting on the system. Now, what do we know? We know by definition, my acceleration is also equal to my time rate of change of the velocity, which is the same thing as v dot. So from here, we can then get a dv dt is then equal to f over m, which is simply equal to a. Now, to solve this first order differential equation, all we're going to do then is multiply both sides, use our separation of variables. So this is our separation of variables. Where we're going to simply multiply both sides by dt. So I'm going to get a dv is equal then to a dt, and then we're going to integrate this side from my initial velocity to my final velocity, integrate this side from my initial time, I'm just going to call that 0, to my final time of t. Now again, since the acceleration is constant, I'm going to pull it outside of the integral. So I'm going to get on the right-hand side a dt. So integral of dt, of course, is just t. So this is then going to give me v minus v0 is equal to a times t, or v then is equal to v initial plus a times t. Now, of course, from this, those of us who have taken physics 1 will recognize this as simply the first kinematic equation. Good. Now from here, to find our second kinematic equation, or to find our position, we're going to note that our velocity is equal to the time rate of change of the position, which is equal to my initial velocity plus my acceleration times my time. Same thing, we're going to use our separation of variables. We're going to multiply both sides by dt and integrate. So that's how we solve a first order differential equation. So I'm going to get dx integral from x initial to x final equal then to v0 integral dt from 0 to t, since v0 is a constant, plus a integral t dt from 0 to t, because again, acceleration is simply equal to a constant. So cool. So left-hand side, integral of dx is just simply x. So I'm going to get an x minus x initial is then equal to v times the integral of dt, which is simply t, evaluated from 0 to t, which is t. So I get vt. Plus integral of t dt is 1/2 t squared. So I'm going to get a 1/2 a t squared. Or in this case, x then is equal to x initial plus v initial times t plus 1/2 a t squared. So, of course, going to intermediate physics, we know that this is simply our second kinematic equation. And I'll go back to these in just a second. And then finally, we can find our third kinematic equation a couple different ways. We can either combine equation number 1 and equation 2 by simply using the first equation to eradicate the time and then use that into the second equation. Or we can do this a little bit more grown-up way by noting that our position is a function of time. Our velocity is a function of time, which means that we can expand our velocity as actually a velocity is a function of position, which is a function of time. So instead of saying that the velocity is only time dependent, we can say that the velocity is different at every different location, which is, of course, a function of time. So it means our velocity is both a function of position, which is a function of time, which means it's actually a functional. So this thing is actually what we call a functional. So good. So from here, we can then do our chain rule. So we can say in this case then is that our acceleration, which is the time rate of change of the velocity. Well, since velocity is also dependent on the position, our chain rule then says that the time rate of change of the velocity is the same thing as the position rate of change of then the velocity times the time rate of change of the position. But of course, we know the time rate of change of the position is simply equal to the velocity. So it's going to be the same thing then as the velocity times the position rate of change of the velocity. So good. From here, again, we're going to use our separation of variables. So we're going to multiply both sides then by dx. So left-hand side, again, I get a, which is a constant, pull it outside. So I'm going to get a dx from x initial to x final is then equal to v dv integral from v initial to v final. So my left-hand side then is going to be simply a times the integral of dx, which is x, evaluated from x to x0, or x0 to x, I should say. Left-hand side then is going to give me an integral of v dv, which is 1/2 v squared. So I'm going to get a v final squared minus then v initial squared. Or from here, we're going to multiply both sides by 2, add the initial velocity. So finally get my final velocity squared then is equal to my initial velocity squared plus 2 times a times my displacement or my change in position. And we'll notice this as our third kinematic equation. So good. So special case, rectilinear coordinates or rectilinear coordinate system. Everything's happening in one direction. As long as I have a constant velocity, of course, pops out our kinematic equations, which we already knew from physics 205 or introductory physics. But again, let's recap each one of these. So again, equation number 1. My final velocity is equal to my initial velocity plus my acceleration times time. We already know this, but I'm going to rewrite it anyway. So what this one tells me then is we can determine v at any moment of time given our initial velocity v0 and our acceleration a. Good. Kinematic equation number 2. X is equal to x initial plus v initial times t plus 1/2 at squared. So again, we already know this, but all this thing says then is we can determine the position at any moment of time given our initial position, our initial velocity, and our acceleration. And finally, the third kinematic equation simply says that the final velocity squared is equal to the initial velocity squared plus twice the displacement. It's going to write it as delta x in this case. And again, we already know what this means. We're going to write it down anyways. So this says that we can determine our final velocity at any position given the initial velocity, the initial position, as well as the acceleration. So again, the third one is just a linear combination of the first two, just eradicates then the time, and that's pretty much about it. So life's great. So good. So let's do a couple examples of this. And good. So the first one simply says that we have a block that is free to slide down a smooth, frictionless inclined plane that is inclined at an angle of theta relative to the horizontal. So good. So let's draw a picture here. So here's my, if I can draw a straight line, there we go. There's my inclined plane. This is at some angle of theta, and let's say my plane or my mass starts off up here. Okay, so this is my block. That's my angle of theta. Says that if the plane or if the height of the plane is h, so this is some height of h, the block is released from rest at the top. What would be the speed when it reaches the bottom? Okay, so we want to know by the time it gets down here. If this guy is released from initial velocity equal to 0, what then is going to be its final velocity by the time it reaches the bottom? Now, we haven't talked about energy yet. Of course, we know energy from introductory physics, but we could use conservation of energy, but we just came up with kinematic equations. So let's use our kinematic equations. So good. So in this case, let's look at this guy. So first of all, let's look at the sum of the forces acting on him. So what do we know? So we know we have mg down in this direction. We have our normal force in this direction. And since it's frictionless, that's it. Awesome. So from here, we can then choose our coordinate system. Since it's accelerating down the plane, I'm going to call that then my x direction, which forces this then to be my y direction, which makes this the angle of theta. So Newton's second law then says that the sum of the forces in my x direction are simply then going to be the mg times sine of the angle. And then that's going to be equal then to what? M times A, which means that A then is going to be equal to g sine of theta. So that's then my acceleration. Now we want to know in this case then is what? What's the velocity by the time it reaches the bottom? So in this case, the easiest one to use then would be simply what? The third kinematic equation. So I know that my final velocity squared is going to be equal to 0, my initial plus g times sine of theta times then delta x, where delta x then is going to be simply what? The length of the plane. Right? So then times L. But again, we can rewrite L in terms of h because we know that what? Using sine then is equal to the opposite side divided by the hypotenuse is then equal to sine of the angle, which means h then, or L in this case, is going to be equal to h over sine of the angle. So this then tells me that my final velocity squared, do it, there we go, final velocity squared is then going to be equal to simply g sine of theta times h over sine of theta, which means these signs are going to cancel. So finally, my final velocity is going to be equal to simply the square root of g times h. Great, so it's going to be my velocity by the time it reaches the bottom. So good, so that's our first example. Our second example then is we're going to do the same thing, but now we're going to have that it's a rough surface. So now, again, here's my inclined plane. There we go. Angle of theta. Again, block starts off at the top. Mass V0 is equal to 0. But now this guy is going to have some sort of coefficient of friction, right? So in this case, a coefficient of kinetic friction, which we're going to call mu sub k. So it wants to know, simply in this case, what is the acceleration down the plane? And then we, just want to know the acceleration. Then we'll have some follow-up questions about that. So good. So let's look at this case. So again, let's use our free body diagram. So we know we have mg downward. So this is my mg. We know that this guy's going to be sliding down the plane. So my acceleration is going to be down the plane. So it's going to be my x double dot, which is equal to a. We also know we're going to have a kinetic friction up the plane. So it's going to be my kinetic friction. And we're also going to have our normal force, where our normal force is going to be up in this direction. So let's use our coordinate system. So it's going to be my x direction down the plane, because that's the direction in which it's accelerating. This is then going to be my y direction, and this is going to be my angle of theta. So good. So let's split this up into directions. So we're going to have the sum of the forces then in the x direction, and then going to be equal to m times a. So here we have two forces. So we have the mg sine of theta down the plane minus my friction force up the plane, then is equal to m times a. Some of the forces in the y direction are equal to 0. Now, in this case, of course, we need the y direction because, just to remind ourselves, that the friction force is, at least for this kinetic friction, is always the coefficient times the normal force is equal to ma. So here we have two forces. We have the normal force upward, and then we have the cosine portion of mg down the plane. At least not down the plane, but in the perpendicular direction. There we go. Pointing downward. So in this case, my normal force then is going to be simply mg cosine of theta. So let's plug that in. So from here, we're then going to get a what? Mg times sine of theta minus mu sub k cosine of theta is equal to ma, which means the m's are going to cancel. Fantastic. So my acceleration then is going to be simply g sine of theta minus mu sub k cosine of theta. Perfect. So let's say that what we want to know as a follow-up question. So this is first example. So let's do another example, which says what then has to be the coefficient, or at least in this case, let's say another question is, for what angle, let's call that the angle of, I don't know, let's call it phi. So what does the angle phi have to be of my plane for this guy to slide down at constant speed? So in this case, we want our velocity to be equal to a constant. So what does our angle have to be in this case? So for this to be true, we want theta then to be equal to phi. So let's talk about that guy. So cool. So let's do that. So first case is that what? Well, first things first, if my velocity is equal to a constant, that means my acceleration then is equal to 0. So using this expression, we get 0 then is equal to g sine of theta minus mu sub k cosine of theta. So in this case, of course, g is a constant, so let's get rid of the g. So this tells me then that what? We're going to have a tangent of theta is then equal to mu sub k. Actually, let me not call that theta. Let me call this phi, since I already called it phi. So phi, there we go, phi. So tangent of phi is equal to the coefficient, which means that the angle then is equal to the inverse or arctangent of the coefficient, right? So in this case, for this guy to be sliding down the plane at a constant speed, we have to have that the angle of the plane is specifically equal to the arc or inverse tangent of the coefficient of friction. So cool. So what does this mean? So this means that if the angle of theta is greater than the angle phi, what's going to happen? Well, this guy's going to simply accelerate down, right? So in this case, my acceleration will then be positive because it's going to be at too great of an angle. So in this case, it's going to speed up down the plane. And of course, if my angle theta is less than the angle of phi, it's not going to move at all, right? So in this case, my acceleration would technically be 0, or less than 0, I should say. It should be negative, which means that if the initial velocity is equal to 0, then it won't move. So in this case, it won't move. Because just because the acceleration is negative doesn't mean it's going to accelerate up the plane, and that would just be, cool and weird simultaneously, right? So in this case, of course, it's not going to move, but if I give it some non-zero initial velocity, so in this case, let's say I give it some initial velocity, which is not equal to 0. In this case, it'll start off slowing down the plane or going down the plane, but it's going to slow down and stop. So in this case, it will slow down and stop. Perfect. So good. So these are some examples of constant acceleration. So let's look at our second case. So our second case in this case, of course, is going to be when our second derivative is not equal to a constant anymore, which means it won't be equal to a anymore, right? It won't be equal to some sort of constant, but instead it will be equal to some sort of time-dependent acceleration. Oh, cool. So let's look at this case. So what happens in this case then? So using our same thing as before, we're now going to have that our first derivative of the velocity will be equal to this time-dependent acceleration. So again, using our separation of variables, we're going to multiply both sides by dt. So then I'm going to get my left-hand side will be dv, integral from v initial to v final, is then equal to the integral of the time-dependent acceleration integrated over time from some initial time to some final time. So cool. So my left-hand side, of course, is just going to be the integral of dv, which is v. So I'm going to get a v minus v initial is then equal to, well, in this case, since we don't know the functional form of the acceleration, meaning I have to know exactly how it depends on time, I can't actually do this integral, which means in this case, I have to leave it as simply an integral until I know the functional form of the acceleration. Or finally, I can write this as v is equal to v initial plus then this integral. T, T, T. So good. So from there, we can now find the position as a function of time. Again, noting that our velocity is equal to the time rate of change of the position, which again is equal to the initial velocity plus the integral from 0 to t of a of t dt. So how are we going to do this one? So in this case, again, we're going to use our separation of variables, integrate both signs with respect to t. So my left-hand side is going to become the integral of x from the initial position to the final position. My right-hand side then is going to become equal to the initial velocity, which is a constant, integrated over time from 0 to t, just like it was for a constant acceleration. But now life becomes a little more complicated. So now I'm going to have a second time integral of my acceleration, which basically means that we're going to get a plus integral from 0 to t dt, integral from 0 to t. Yeah, let's see. How do I want to do this? 0 to t, and then I'm going to do a integral from 0 to t of a of t dt. Now, from here, actually, I'm going to put a prime on this guy and a prime on this guy. Okay. So initially, what I'm going to do is I'm going to integrate the acceleration to some time t prime, and then I'm going to integrate that, which now depends on t prime, to the final time of t. So basically, whenever I have a non-constant acceleration, we are going to have two integrals on this last term where we have to integrate the last term over time twice, where the first time we would integrate over time to get the velocity, and then the second time we would use that to get the position. Now, this is very similar to what we did before. We integrated that term twice, but since it was independent of time, we got an integral for just t the first time, which gave us a t, and then the second time, that's where we got our t squared. But in this case, since we need to know this functional form, we would then integrate for this functional form, knowing exactly what this guy is, and then we can determine the total for him. So good. So let's use this. Let's do an example. Let's see how this guy actually works. So let's say that we have a particle which is moving with some mass m equals 1, and it's moving in one direction so that the net force acting on this guy is equal to a time-dependent force, which is then equal to some constant k, t, e to the minus alpha t. What'd I do? I don't know what I just did. There we go. Okay. Sorry. Now, in this case, we're going to take our constants as k is equal to 1 Newton per second. And we need that because what? Our force is a Newton. And we have a second coming from the time. So that guy has to have units of Newton per second. And then finally, we're going to use that alpha is equal to 1/2. We're do that again. 1/2. Would you stop? Seriously. Okay. Alpha is equal to 1/2. It really doesn't like me writing them. One more time. Alpha is equal to 1/2 per second. Get rid of the second in the numerator over here. Okay, so it tells me that further, my initial velocity is 0, and we can say the initial position is also at 0. So what does it want me to do? It wants me to calculate the position, speed, and acceleration as a function of time, and then plot them as well. Okay. So in this case, I'm mostly just going to do everything algebraically as usual, and then I'm going to plug in my numbers at the end of the day to get the actual plot. But we'll talk about what the plot looks like here as a function of each one here in a second. So let's start off with the acceleration. So what do we know? We know the sum of the forces acting on the system must then be equal to the mass times the acceleration. Now, what else do we know? We know the net force acting on our system is simply f of t. So we get f of t then is equal to ma, which means the acceleration then is going to be equal to f as a function of time divided by m. Putting everything in, this gives me k over m times t e to the minus alpha t. So this then is my acceleration as a function of time. Right? So cool. So let's think about the plot of this guy. So what do we know? We know that k over m, of course, in this case is just what? 1, but this is just some constant. We have t, which means if I'm trying to plot this guy, t wants to grow linearly, especially for small time. So that means t wants to do something like this, right? This is our t portion. So what we know is that near 0, right, when t is approximately around 0, we know that the exponential is just going to be 1, right? So that means initially for small times, this thing is going to follow just this linear t. Then what else do we know? We know that also k over m, this thing has an exponential. So here's my exponential. Something like that. Now, as time goes on to infinity, what's going to happen then is the exponential is going to take over because that's decreasing faster than the linear portion is increasing, which means our plot is going to initially follow the linear portion, and then it's going to follow then the exponential afterward, which means our total plot is going to look something like that. So let me plot this one more time. So we can kind of see what it's doing. So this is my time, this is my acceleration. So this thing is going to follow linear, and then it's going to turn around and then follow the exponential until it goes all the way back to 0. Okay. So this is my acceleration as a function of time. Right. So good. So let's look at our velocity. So what do we know? We know our acceleration is equal to the time rate of change in the velocity. which means, again, using our separation of variables and then integrating, what are we going to get? So we're going to get that our dv integrated from our initial velocity, which is 0, to our final, is then going to be equal to my integral from 0 to t of a dt. So my left-hand side is simply going to be v, because the integral of dv is v, evaluated from 0 to v, which is v. So this guy's going to be equal to k over m, integral from 0 to t, te to the minus alpha t dt. Now, from here, I got to teach you some tricks because, you guys know me. I love my math tricks. So let's teach you some math tricks here. So in this case, there's two ways I can do this. I could either integrate using integration by parts, but that's no fun. So let's talk about a different way we can use this. So I believe this is called the Feynman trick, but don't quote me on that. But notice that if I took e to the minus alpha t, and then I took the derivative of that with respect to alpha, this guy then would give me a what? Minus t e to the minus alpha t. So what I can do in this case then is, instead of using integration by parts, I can use this in here to then rewrite this integral in terms of the derivative with respect to alpha. So what do I mean by that? So what I mean is that this guy's going to become minus k over m, integral from 0 to t, dd alpha of e to the minus alpha t dt. Now, in this case, alpha is technically a constant, but I'm treating it as a variable, but it is not dependent on time, which means that what? I can pull this alpha term, or at least this derivative of the alpha, outside of my integral. So this guy's going to be the same thing then as minus k over m dd alpha of then the integral from 0 to t e to the minus alpha t dt. So what does that mean? So that means that instead of using integration by parts, I can actually do this integral of the exponential, which is actually a really easy integral. And then after that, take a derivative with respect to alpha. And then we get the final answer at the end of the day. So this is a cool, nifty little trick. So let's do that. So this is going to be then minus k over m dd alpha of. So what do we have? So we have the integral of an exponential, which is the exponential back divided by then the derivative of the exponent. So I'm going to get a minus 1 over alpha e to the minus alpha t, evaluated from 0 to t. Okay. So that's going to give me that my velocity is minus k over m. And then we're going to get a dd alpha. And then let's plug in. So when I plug in t, I get this thing back, right? And then when I plug in 0, I get a 1. So I'm going to put the 1 out front, right? So let's do that. So I'm going to pull out that alpha there. Okay, so let's pull out that 1 over alpha with the negative. Actually, I'm going to keep the negative sign. So I'm going to get a 1 minus e to the minus alpha t. So again, putting that negative sign in there basically just means that what we're going to have that becomes a 1 out front. Or I could switch the order with that other negative sign out front, but let me not do that yet. So good. So now all I want to do now is take this derivative here with respect to alpha. So good. So I have a product of two functions. So first one is what? 1 over alpha. Take the derivative of 1 over alpha. So that's going to become equal to what? A negative 1 over alpha squared. So I'm going to get a minus k over m. And then I'm going to get a minus 1 over alpha squared times the second term, which is e to the minus alpha t, plus the first, which is 1 over alpha, times the derivative of the inside. So the first part, alpha, of course, the derivative of 1 with respect to alpha is 0. And then I'm going to get derivative of this guy. So I'm going to get a what? E to the minus alpha t all times t. Because the derivative of the exponent with respect to alpha is a negative t, right? And then that negative is going to cancel out the front guy. So let's do all that. So now let me bring that negative sign on the inside. So I'm going to get a k over m times. So we're going to get a 1 over alpha squared, 1 minus e to the minus alpha t, plus 1 over alpha t e to the, actually I brought in that negative sign, so that's going to give me a negative. Sorry about that. So minus 1 over alpha t e to the minus alpha t. All right, let me leave it that way. Okay, so this is my velocity as a function of time. If I want, I can rearrange this guy a little bit further, but I'm just going to leave it this way for now. Okay. So cool. So what's going on here? So what do we know? So let's think about the plot of the velocity versus time. Let's talk about what this thing is actually doing. So my velocity versus time. So here's my time, here's my velocity. So first off, what do we know? We know that what? Initially, what's happening? So when t is equal to 0, so this term here is going to go to 0 because I'm going to get a 1 minus 1, which gives me a 0. And then I'm going to get this exponential term, which is growing, right? So again, this guy's going to grow basically linearly initially. So this guy's going to grow linearly. So I'm going to get something that looks like this, right? A little bit of quadratic on there, but that's fine. And then as time goes on to infinity, what's going to happen? So this term here, again, is going to go to 0. This term here is going to go to 0, but this whole thing then is going to go to simply a constant, where this is my constant term, right? So this thing is going to basically do this, right? So it's going to asymptotically approach this constant, where this constant then is going to be a k over m alpha squared. So this is my velocity as a function of time. Okay, so this thing is going to initially kind of go linearly, because again, this term here is going to be the surviving term. And then again, as time goes to infinity, both this term and this term are both going to go to 0, which means I have simply that constant term. So finally, to get our position, we would then use that what our velocity is equal to the time rate of change of the position, which again means that separation of variables says that we're going to integrate the position from the initial position to the final position. And we're going to integrate the velocity with respect to time from the initial time to the final time. So that big monstrosity that we had initially, we're going to put that in here. In this case, I am going to rearrange it a little bit. So my left-hand side, of course, is going to be the integral of x, which is, or dx, which is x. So I'm going to get an x minus x initial, but x initial was simply 0. So let me put that in here, actually. So my left-hand side is just going to be x. And then this side is going to be equal to the integral from 0 to t of, so k over m, which is a constant. So we pull that out front. And then we're going to get a 1 over alpha squared. So here I'm just going to combine terms together, times 1 over alpha t plus 1 over alpha e to the minus alpha t dt. Awesome. So in this case, let's kind of rearrange. So I'm going to get a k over m times. So I get a 1 over alpha squared integral dt from 0 to t. So that's nice and easy. That's the first term. And I'm going to get a minus 1 over alpha integral t dt. Well, let's do it this way, actually. So I'm going to get a t e to the minus alpha t dt. So that's the second term. And then finally, we're going to get a minus 1 over alpha squared integral from 0 to t of simply e to the minus alpha t dt. Now notice that this term here, which is the second term, is actually exactly equal to the original integral that we did, this one, right? Which means that this trick that we did here is still the same, which means all of the stuff here we can simply take and plug right in, and we get exactly that portion of the answer, since we already know exactly what that is. So in this case, that's all we're going to do. We're going to simply shove that in there and then do this integral, but we'll finish this off in class because I'm basically out of time. So yeah, so we'll plug that in, we'll finish this off, and then call it a day. All right. So we'll do that on Wednesday. And then we'll start looking at some curvilinear coordinate systems and how things change in those cases. So yeah, as always, let me know if you have any questions, and we'll talk about it quickly on Wednesday, and then we'll pick up from there. All right. So I'll see everybody then.